Hi Year 12s, we're back and we're doing our last exercise pretty much of the year. It's called Objective Functions, exercise 23D. I'm going to give you a chance to copy down the notes again, pause the video when you need to, copy down the notes, and then I'll explain it in a sec. Excellent. Alright, so an objective function, it's pretty much an equation and we either want to maximise it or minimise it. So it's like the equation that we go by in any question. I'll show you what I mean. So I've said here in notes, we want to maximise it. So if it's a profit objective function, we obviously want to maximise our profits. If we're running a business, we want to make the most money that we can. Or if it's something like how much paint do we need to paint a house, you want to minimise it. So obviously you don't want wasted paint. So an objective function can be either maximised, depending on the question, or you want to minimise it. Okay, so what does it mean? Again, we're using the corner point principle. So I said here the maximum or minimum value of an objective function will occur where at one of these corner points. So if you have a look, so any of these points inside the feasible region, they all satisfy the equations. But when we maximise or minimise the objective function, it always occurs at a corner point. So one of these points here. So in this case, you can see the feasible region, and they're the four corner points that are given. So it says here, find the minimum value, so it tells you they want the minimum value of the objective function. And they've given you the objective function here. So it's z, is the objective function, is equal to 3x plus 2y. So what we have to do is for each corner point separately, so the first one we'll do is 0, 12. 0 is the x value, 12 is the y value. So if we come over here, it says here at each corner, we use the coordinates to find the value of the objective function. So all we do is substitute the x value and the y value into that objective function, and in this case it says to minimise it. So x is 0, so 3 lots of 0 is 0, and y is 12, 2 lots of 12 is 24, and we get our answer is 24. We substitute the points therein, we get 14, 17 and 42. So it's very simple substitution, and we wanted to minimise it. So we have a look here, and this one here, 14 is the lowest value for our objective function. So the minimum value of z, our objective function, is 14, and it occurs at the point 24. So that is all you have to do for that. Good job. Hi everyone. So the next little example we're doing is about integer solutions. So again, I'll give you a chance to copy down the notes. Pause the video when you need to. So as we talked about last lesson, integer solutions are points within the feasible region that have to be whole numbers as coordinates as well. So all these dots, so I said here, sometimes we only use the coordinates that are whole numbers in the feasible region. So given this example, so here's our feasible region. So normally we'd shade in that whole region and say any point within that region is a solution. However, when it says an integer solution, it only wants the whole numbers. So remember, if it's including these lines, then the points on those axes or on those boundaries are included. But in this case, it's just an example. We've got the two axes not included, and then that line across there. So all the whole numbers, all these points represent the whole numbers. That might be 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, and so on. So you have to do this very accurately on a graph, and then find all the points. So I said there, we can consider each dot in the feasible region in order to answer the question. So in this case, all those dots are solutions to that question. Alright, that's pretty much the theory done. So one of the examples I want to explain, example 8 on page 760. So this worded question, and it said x is the number of large vans and y is the number of small vans. So from the information in the actual question, you can work out x must be greater than or equal to 0, because it's the number of large vans, and the same with the number of small vans. So those two are easy equations or constraints to make. Now the next one is something to do with the number of parcels. It says it in the question. You should be able to, this is the hard bit, you've got to be able to work out this equation. 150 times x plus 60 times y is greater than or equal to 900. So that equation had something to do with parcels, and the next one had something to do with cost. 5x plus 4y is less than 44. So you have to read the question and be able to come up with those constraints. One thing to note with this equation, we can simplify it to by taking out a common factor, and you get 5x plus 2y is greater than or equal to 30. So you can use either of those two equations, they're the same. Alright, so once you can actually read the question and get these four constraints, then you get your graph and you plot it on your graph. So there's that, the first equation, the big one there, is that line across there. Notice it's a solid line because it's equal to, and here's this equation there, and it's a dotted line because it's not equal to. Okay, you do the test point again like normal, and we've come up with our feasible region is this little section inside here, and it actually includes the x-axis as well. So when you do this accurately, you'll get a whole bunch of points, which are called integer solutions within that feasible region. So remember, if it says it wants integer solutions, because in this case, x and y are the number of large vans and small vans. You can't have 2.5 vans that you require, so that's why they must be whole numbers. So in practical questions like this, you just got to use common sense as to whether they're whole numbers or not. So sometimes the question won't state, find the integer solutions. You just have to realise that because it's a number of vans, so it must be whole numbers. Alright, so you get a whole bunch of points, and there are all the answers. And I think the question said, find the largest number of vans required in this situation. So, if we look, we've got 4 different points. What you need to do is find the coordinates of each of these points within that graph. So when you do it accurately, you'll find the coordinates of each point. So these 4 points, when you add them together, so remember x is the number of large vans and the number of small vans. In this case, from that point, it's 4 large vans and 5 small vans, which totals 9 vans in total. And then there's 5 and 4, which totals 9. 6 and 3, and 7 and 2. So in any of those cases, they're all equal, they all add up to 9 vans. So the total number of the largest number of vans that we can use is 9 vans. And the question also said find the smallest number of vans that we can use. So the other coordinate we use is 60, because it's in one of these points, so when you read them accurately, so you can see the point here, 60 is there. So when we use the point 60, 6 plus 0 is 6, so 6 vans is the smallest number of vans that we need to use. So to answer the question, the largest number is 9, because when you add the coordinates together, you get 9, and when you add 6 and 0 together, the smallest sum is 6. Good job. Hi guys, I just wanted to go through example 9. Now it's one of the trickier questions. You need to read it in the textbook first, and I've copied this bit out from the question. So you can read the question as a potter and an artist to make these vases. There's Ming type and geometric type. That's how many hours it takes. This is all in the question. Firstly, copy it down, and then I'll explain the question. Alrighty, so as I said, this is one of the harder questions. All that information is in the question. I'm not going to do every single part of it, but I'm going to explain most of the question. Okay, so it already tells you, gives you the constraints that x must be greater than or equal to 10 and y must be greater than or equal to 20. And then it tells you, so they're the constraints relating to the number of vases. Then there's constraints relating to time. Now it says the potters. The time for the potters is 8 hours for the Ming one, so it's 8x plus 4y, and it says it must be less than or equal to 400 hours. So that's how we get that equation, but that was actually given to you. Now the first equation that it's asked, the first question is asking for, it says the total time available for the artist is 160 hours. Write this as one of the constraints. Okay, so we've got 2 hours for the Ming ones, for the artist, so that's 2x. Plus, it takes 2 hours for the geometric ones, so it's 2y. And it said the most time we've got is 160 hours. So So it must be less than or equal to 160. So that's how we get it. So it's very similar to the other one that was given, and it's just prompting you, it's asking you for the next constraint. So that's how we get that one. Alright, now we get into the trickier stuff, or the meaty stuff of the question. So now part B says, draw these equations on a graph and find the feasible region. Okay, so the first one, x equals 10. We find x, and there's 10, and it's a vertical line that goes up there. I should be labelling all these, but I'm not going to just for the sake of time for this graph. Y is equal to 20. So y is equal to 20, goes across there. There's our next constraint. And by the way, it says x is greater than or equal to 10. So it's greater than, which is this side. And then y is greater than or equal to 20. So there's our graph, and it's above that. So far, we've got our feasible region is this section here. Okay, so it does get a little bit complicated. Next one, we've got 8x plus 4y equals 400. So, and the other one is 2x plus 2y equals 160. Okay, so I've got them right here. So we can draw our two graphs. So this one, they're both straight lines. They're both 4 lines. Whoops, didn't do that very straight. And the other one goes across there like that. Did I draw that? Okay, that was alright. It's not too bad. Alright, and now that we've got our graph, we have to find the feasible region. So remember I said it's already above that line and to the right of that line. And we need to work it out from these two lines where it is. You can do that to a test point, 0, 0, like always. I may as well just do it real quickly. So the black one, here, the test point for this one, we'll use test point 0, 0. We get 0 plus 0 is less than or equal to 400, which is correct, because 0 is less than 400. And the purple one, 0 plus 0 is less than or equal to 160, and that is correct as well. Alright, which means that the point 0, 0 is in the feasible region, so it means it's below that line and below that one there as well. Which means that the region that we require, so it's above that one, it's to the right of that line, it's above that line, it's below that one and below that one, so here is our feasible region. So just make sure in a SAC or a test you do this very clearly. So there's our feasible region. Excellent. So what have we forgotten to do? We must always label the corner points. So that one there is 1020. So make it nice and clear. There's a point. This one is 10. Okay. So this one's 1070. Oops, let's write that there. And you can do this manually or on the CAS. Hopefully you know how to work out those. We've done that before. This point of intersection there is 2060. And the one down here is 4020. So you can use CAS to work out those corner points if you like. So now that we've got our corner points, we've got our shaded feasible region. That's the next bit. Okay, so C just said shade the feasible region, which we've just done. Alright, now question D says, all the vases are produced in a week are sold. Write a profit expression or an objective function. So the profit, and it says in the question that they make $50 profit for the mean ones and $30 profit for the geometric ones. So the profit equation is profit equals 50x, 50 times the number of mean vases, plus $30 times by the number of geometric vases. So there's our objective function, which is profit. And obviously you want to maximize the profit. So there's our equation. So in the next part, it says, determine the number of each type of vase that should be produced in a week to result in the maximum profit. So obviously, as soon as you see profit, you want to maximize it. So again, to find the maximum profit, you're substituting each corner point. So our 4 corner points are there, so I've listed them there. Alright, so we use that equation. So profit equals 50 times x, 50 times 10, plus 30 times 20. And you write all those down, and it's pretty simple. So this one equals 1100. So you do the same for the next one. So you're substituting x equals 10 and y equals 70, and you get 2600. I'm not going to show the workings out for these. Profit for this one is 2800, and the profit for the last one is 2600. Okay, So they're the profits for each of those corner points. And it says to maximise the profit. So which one's the maximum? It's this one here. So the profit, so then you answer the question in words, the maximum profit can be found when we sell 20 Ming and 60 geometric ones, and the profit is $2,800. So answer that in words. Part F just says, for some reason you can only make a profit now of $25 for the geometric ones. Now write an equation for the profit. So it's exactly the same as the objective function for the last one. $50 profit per Ming vase, but you only make $25 for each geometric one. You write down the 4 corner points and do the exact same process. So part E and part F are the exact same question, just with a slightly different objective function. So I've kind of explained roughly how to do that question. You really need to read the question and understand how to come up with those equations. And once you go through the process, you can draw the graphs, find the feasible region, corner points, substitute them into the objective function, answer the question in words. Good job everyone, see you soon.